Hello all. Once again, thank you for everyone that's joined the call so far. There's still quite a few more people filing into the webinar as we speak, so we're just going to wait a few more minutes prior to getting started. Thank you again. Okay, thank you for everyone who's joined our webinar today, and welcome to our introduction to generative technology within Fusion 360. So my name is Matt LeMay. I will be your presenter today. So my role at Autodesk is as generative adoption. So I work with all of our customers to understand how to use generative and additive technology effectively. I have 3 years experience at Autodesk, and I'm a trained mechanical engineer. And prior to joining Autodesk, my experience was in aerospace composites and additive manufacturing for the medical industry. I am located in our Massachusetts office. So as many of you might imagine, I'm a very large Patriots fan, and hopefully that doesn't offend anyone too much. So for the presentation today, again, it's an introduction to generative technology. So what we would really like to come across, or what we would really like to provide you today, is an introductory knowledge to generative technology. Second would be to help you learn how to access generative technology within Fusion 360. With that, we'd like to help you learn what some of the most common generative workflows would be and what some of the considerations that you might have to make if you were applying this technology to your products. And then more importantly than that is how to find additional help and support after the webinar that we have today. So certainly no one no one is going to become an expert just by watching this 1 hour webinar today. So we'll provide you with other options of how you can become an expert and how you can. Everyone will be on mute. However, we will have about 10 to 15 minutes at the end of the webinar where you can raise your hand and ask questions live. So in the meantime, please feel free to use the chat window or the Q&A tab to type in your questions, and then we can answer those at the end of the presentation. So moving forward to take a look at the agenda for the presentation today, we'll start off with a quick introduction to what generative technology means and why Autodesk is moving in this path. We'll then spend a couple minutes to talk to you about what you would need in order to get started using generative technology. And then we'll spend the majority of the presentation on reviewing a sample project from start to finish, showing you all of the workflow requirements needed to successfully produce a project. And then again, we'll leave about 5 to 10 minutes at the end for closing, next steps, and Q&A. So prior to moving into the introduction to generative, I'd like to launch our first poll question. And this should be coming up on the screen just now. The question is, what is your current level of experience with Autodesk generative technology? And that could range from none to advanced. So we'll wait about 5 or 10 more seconds here for the rest of the answers to come in. And closing the poll now, it looks like the majority of the people here on this call are pretty new to generative technology, and that's exactly why we present all of these webinars and why we'll provide you with some additional training resources after the presentation as well. So to get back into the presentation, again, first we'd like to cover an introduction to generative technology and what's really leading Autodesk towards this path. So as we take a look at the manufacturing industry and really CAD in general, so Autodesk has been making computer-aided modeling solutions for a little over 35 years at this point. And CAD has always been a way for us as a team of engineers to take the ideas that we have and really to put them down on paper. So we've always been constrained on the ideas that we can have as engineers, and then also the manufacturing processes to actually produce those components. So we've always been constrained with things like casting, injection molding, all of those processes, and what we can think of as engineers has constrained the type of products we can create. As we look towards the future and we look at the growth of additive manufacturing, we really need a brand new way to help us think about all of these new possibilities. So additive manufacturing and 3D printing can allow us to create just about anything. So we need a new way to help us think about all of these possibilities that are now available to us that were never in the past. So in this sense, we need generative technology to really be a co-creator within this process where we can outline our higher level requirements, and generative can present us with tens, hundreds, or thousands of options that we can then explore. So as we take a look at the process that we're actually trying to adjust, this is the traditional product cycle that we've seen from many of our customers. So it starts with taking a small handful of concepts, maybe 3 or 4, and then evaluating those concepts for their structural integrity, for their manufacturability, to the point where we're eventually bringing a product to market that could have taken us longer than we would have hoped. And we're also taking a product to market that in some senses may be compromised since we're not exploring a wider range of options to produce. The entire idea with generative is, as the first step within this process, to generate tens, hundreds, or thousands of validated and manufacturable options that we can then start to explore and then move forward with. So here you can see we're generating a wider range of options. We're generating things that are ready for additive manufacturing, ready for subtractive, and we also know are validated for the structural integrity that our project needs. So the goal with generative technology is to allow us to bring products to market quicker, products that we wouldn't have explored in the past, and also products that we as engineers, and you can see this if you look at that image to the right, would probably never thought of on our own. So when we look at the main advantages we're trying to get with generative technology, again, the first one is that idea about exploring a range of options. So with generative technology, as we set up our problem and as we start to generate, we can quickly get tens, hundreds, or thousands of options to explore. And here we can start making trade-offs that we might not have made in the past. So we can make trade-offs for what kind of material to use, what level of performance we'd like, and even what kind of manufacturing that we'd like to produce our components with. Second would be planning for additive manufacturing processes. So we talked about the growth of additive manufacturing throughout the industry, and generative is a great way for us to start to explore options that might only be possible through additive manufacturing and start to make those trade-offs as well. And then the third point would be part consolidation. So using generative technology, we can take expensive assemblies that are maybe 10, 15, 20 components and generate options that can consolidate those expensive assemblies to one single component. So to take a look at what some of our customers are using generative technology for, this is a great example from General Motors, and I'm sure many of you have seen it as well. GM took this conventionally produced seat bracket assembly that you see in the top left of this slide, and they started to generate options to consolidate that 8-part assembly into just one single component. So eventually they were able to generate that assembly from 8 parts to one. The generated part is also 40% lighter and 20% stronger. And probably more important than anything that we've talked about so far is that they not just generated one single option, they generated 150 viable options that they could then start to explore and make trade-offs from. So to show a little bit about how that process went, this is how our generative solver works. It will take the entire volume that our generated part can fill, and it will either add or subtract material away from that to reach the structural and manufacturing requirements. So here you can see the entire range of options. Again, to that point that GM wasn't trying to just optimize for one single component. They wanted to view the entire space, the entire range of options. So there they were able to look at 150 viable options. So as we start setting up generative projects, the first thing we always need to do, and you can see this in the video now, is take our existing assembly environment, and we need to think about what are our keep-in geometries, which we call preserves, and what are our keep-out geometries, which would be our obstacles. And from there, you can see GM was able to take their 8-component assembly and replace it with one single part. So another example that I'd like to show today too, this is Wheel, a personal mobility company. And they took a very similar approach, just on a larger scale and for a very unique product. So they were looking for the frame from one of their personal from one of their personal mobility devices, and it's a part that has pretty high structural requirements. It's also a pretty costly part for them to manufacture. So setting up that geometry space, like we talked about, calling out those preserves and the keep-ins, calling out those obstacles, which are the keep-outs, they could then start generating options that they probably wouldn't have thought of in the past. So again, very quickly, you can see the entire range of options shown here on this graph. Something we haven't really covered too much yet on this process is the most important thing with all of these parts that we're generating is that all of these are usable CAD geometry in the end. So we're not simply generating a mesh, we're generating usable solid CAD geometry that we can bring right back into Fusion. We can move right back into our assembly, make any adjustments that we need, and then move this further towards a production phase. So here you can see we're making some slight adjustments to the generated model. We're running an FEA on it to validate everything we've done. And then we could even bring this to additive or subtractive processes to produce. So when you actually look at what projects would find the most value from generative, what we've typically seen is that any time you need to bring a new product to market, generative can add value. So if you have a new project to create, generative can allow you to look at questions like what kind of material is needed. Generative could provide you with a guide that you could then model over. Or if you're looking for things like additive manufacturing outputs or subtractive outputs, generative can produce production ready components for you. Second would be parts consolidation. So we talked about this a little bit earlier. And as you look at some costly assemblies you might have, generative is a great way to explore some cheaper options for that to reduce on supply chain. So here you can explore those costly assemblies again and then generate an option to replace those multiple components. And the third piece would be a part enhancement application. So you can take existing components that you might already manufacture, you might already have out there in the field, and you can generate alternative options for that to maybe make trade-offs on material or to replace it with higher performing components. So just to summarize the introduction on generative technology, so what's unique about generative technology within Fusion? So the first thing is exploring a range of options. So typically with optimization technologies, we have one set of inputs and you get one specific output. With generative within Fusion 360, we apply our range of inputs and we can get tens, hundreds, or thousands of options that we can then start to explore. Second would be that it's manufacturing aware. So currently we can put in intelligence for the additive manufacturing process and the subtractive manufacturing process. So we know the options that we get back are ready to be manufactured within those cases. The third piece would be we can explore a range of multiple materials. So within one generative solve, we can view results for up to 10 materials. So you could look at what trade-offs from aluminum to titanium to steel might look like and how they would affect the actual structure of your component. And then finally, we talked about this a little bit as well, is that probably the most important piece is that what we're generating is not just a mesh, it's usable solid CAD geometry that you can adjust, post-process, or bring into your assembly to continue to move forward to production. So as we move on to this next section and we talk about how to actually access generative technology within Fusion, I'd like to launch our second poll question today. And we just like to get a little more information on who's viewing the webinar. So the question is, which one of these personas matches your function closest? So it could be an engineer, could be manufacturing, could be education, or maybe you do everything in a little bit of all of these topics that we have on the screen. Okay, and thank you for everyone that answered the question. It looks like the majority of people say that they do everything, which is great. And I think that's something that we'll really cover today is that generative has value to every phase along the product cycle, ranging from initial product creation to the engineering and manufacturing phases. So generative can add value every step along the way. So thank you again for everyone that answered that question. So the next piece that we wanted to cover today was access to generative technology. So Fusion, so generative technology used to only be available to Fusion Ultimate subscribers, and in October that changed. So now generative is available to all commercial Fusion 360 subscriptions. So that is important to note that it is only commercial subscriptions right now, and we do not have access to the education community yet. The second piece to note is that generative works on a cloud consumption model. So we talked about generating hundreds and thousands of solid CAD usable geometry, and we do all of that compute on the cloud. So currently it's 25 cloud credits to generate a solve and 100 cloud credits to load one of those solid CAD geometries back in. And we'll talk a little bit more about what that means within a project later on. Second to that is we do have a Fusion trial that allows you to get access to generative available today. You can see the link on the screen here. And what essentially this provides you is a 1-month commercial trial to generative that allows you to have a small amount of cloud credits that you can use to start working on some of your projects. So we'll talk about this a little bit at the end as well. So as you actually start using generative technology within Fusion, again, one of the main points for the presentation today is to provide you with information on how to get additional training and support after this presentation. So one that I'd highly recommend is the Fusion 360 adoption portal, and I'll share that link at the end of the presentation. Here we have a set of curated videos that walks you through the entire process, talks a little bit about theory, and then a little bit about how to actually complete these workflows within product as well. And then finally, please feel free to email me after this presentation with any questions as well. You can see my email there on the screen, and I'll share with everyone at the end of the presentation. So for the majority of the remainder of the presentation, we'd like to cover a generative workflow within product to show you the entire process that you might take. And prior to doing that, I'd like to launch our third poll question. So we talked a little bit about the advantages of generative technology. Could be planning for additive, planning for subtractive, accelerating product development. Which one of these that we've talked about would apply the most value to you and your business? So we'll leave this open for just a few more seconds. And thank you again for everyone that answered the poll question. It looks like the majority of people, which makes sense, they say all of the above is something that would be valuable. Second to that would be really increasing their innovation capacity. So improving the amount of ideas that a user or maybe the engineer is able to think of through this entire process. So once again, thank you for everyone that answered the question today. So moving on again, for the remainder of this presentation, we'd like to cover a full workflow for a generative project. And the project that we'll be covering today is the GE Jet Engine Bracket Challenge, which I'm sure many people might be familiar with on this call. So about 5 years ago, GE sent out a competition to their community to see how many unique options that they could get for a jet engine bracket. And you can see on the lower right-hand side of the screen, there's a really wide range of options that the community presented to them. And this is exactly that idea that we're trying to achieve with the generative technology approach, is that there's always more than one right answer to an engineering problem. So the community was able to provide GE with a couple hundred different solutions, and we hope to do the same within 30 minutes or a few hours as we set up this problem and then generate all of these options. So as you look at any generative project, it typically follows the same overall workflow. And the first is setting your functional and manufacturing requirements for your project. So here you need to think about what kind of assembly features do you need to consider. So we talked a little bit about keep-ins, which are preserved geometries. We talked about keep-outs, which are obstacle geometries. We also need to factor in what type of manufacturing process we can allow for and what kind of loading conditions that are applied to our project. Second would be taking those functional manufacturing requirements and actually setting them up within the generative solve. So here we can call out that geometry that we've either created for preserves or obstacles, apply our loading conditions, and then set up our objectives to tell generative technology what we'd actually like to achieve through this process. And then we talked about how we're generating hundreds, thousands of options. The final phase is to start exploring and making your choice on which one to move forward with. So for the GE Jet Engine Bracket Challenge itself, the requirements were presented to us. So we knew a specific titanium material that they were looking to solve with. We knew all of their loading conditions on the lower left-hand side of the screen. And we knew that they had some additive manufacturing requirements that we had to adhere from. So as we talked about, the first thing that we always need to do is we need to take our assembly context and create our preserve and our obstacle geometries. So we'll show this all within product as well, but we need to really factor in what are the geometry sections that we know we need to have after our part has generated, and those are our preserved geometries. You can think about that as constant wall thickness around where a fastener might be attached to. And then we also need to think about the obstacle geometries or the keep out regions within our geometry, which you can see at the bottom right. And this could be some other parts within our assembly that we know we need to avoid. It could be moving parts. It could be the fastener locations themselves. It's anywhere we know after we generate our part, we can't have any we can't have any material in those sections. So to get started, we'll open up Fusion 360. And for those of you that are new to Fusion 360, Fusion is a CAD, CAM, simulation, and now generative tool that's all cloud connected. So the idea is to take what used to be a range of separate solutions within multiple different products to have them within one cloud connected package. So the first thing that we would need to do, you can see that we're currently within our model workspace. To start generating a project, we would click on that drop down and click on generative technology. So for this GE jet engine bracket, we would take that bracket and move over to that generative workspace. So the first thing you'll notice is that our user interface will change, and this is the generative user interface. So it's important to know everything within Fusion works from left to right. So we have the ability to set up our solve on the top left. We then have features to edit our model and actually extract some of that geometry and then assembly context that we talked about. We then have the ability to call out our preserved geometries and our obstacles like we talked about. We can then set up our loading conditions, so we can set up our constraints and set up the loads that are actually applied to our project. We can then apply our objectives and our manufacturing constraints, set the materials that we would like for our solve, and then we can start to generate and explore the options for that project. So the first thing that we would do is go to the Edit Model workspace. And again, we need to take our existing component and start to extract those preserves and obstacle geometries like we talked about. So the first thing that I would do is I would copy several of these components, and there's a couple different ways to do this, but I'll just show one of these today. And the first operation that I might try to do would be to extract a constant wall thickness around all of these pins that we know that we need to keep in geometry later on. So to do that, one way would be to create a sketch on the face at the bottom and then just start creating a series of profiles. And again, there's lots of ways to do this. I'll try to show a little bit of everything today. After we've done that, we can just select those profiles. And as we press the extrude key, rather than extruding or cutting, we're going to go through the intersect command, which is essentially just extracting that geometry away. And we will only extract that from one of the copied parts, so we have that original jet engine bracket that we brought in. So after we do that, you can see all of this geometry that we've now created. We've extracted all of those sections from that original part. We can also use some of the quick modeling features within Fusion to then take away some of the geometry that we didn't want. So you can see there's a lip within each one of these profiles. I'm just selecting and then erasing each one of these. So that's providing us with our first preserved geometry. So this is at the end of our generative solve. We know that we need to apply fasteners within all of these locations. So the next thing that I would do is maybe create a component from this, and we'll call this preserves. And that's the first piece that we needed to do. So the next would be that we know that this jet engine bracket needs to attach to a plate at the bottom. So we also need to create geometry to call out other parts within our assembly that we know that we need to avoid. So in this case, I can create a sketch on that lower plate again. And here I'll just create a sketch of a rectangle there. And here we'll just select that profile and we'll extrude that a certain length. And this time we're just creating a new solid from that. So here you can see that plate that we just created is now containing those preserved geometries we've extracted on top of it. So the next thing that we need to factor in is that we also need to create obstacle geometries for where our fasteners are actually going to be located. So within each one of these pins, we know that we're attaching a fastener to it. And we also need to know that we have assembly clearance to that later on. So we showed some of the parametric modeling tools within the Edit Model workspace. So the next one I'll show is actually a surface editing tool. So if we go to the surface tool at the top and we press create and patch, you can see I'm just patching all of these holes within these preserved geometries we've created. Another quick tip within Fusion is that if you right click, it will bring up a quick usage toolbar. So here I can just repeat patch quickly rather than having to move back to that toolbar. And then I'll just repeat this on either side of this preserved geometry here. So after we've done that and we've created a patch on the top surfaces and then on the bottom as well, we can go back to the solid tab and press fluid volume. And as we select all of those features and just select the internal geometries, this is now going to create solid CAD geometry on the inside surfaces of all those pins. So you can see it's now highlighted and we've extracted all of that internal geometry away. So we can call that our obstacle geometry. And again, that's what we know that we need to avoid after we're finished solving. So the next thing that we need to think about, and we can hide our preserves for a second, is to look at assembly clearances as well. So we have the sections created as obstacle geometries for where the fasteners need to be, but we also need to think about the assembly clearance, and we need to be able to get to these sections later on. So we can actually just extrude all of these surfaces up, let's say about 1 inch, so that we know that after we're finished generating this part, that we can actually access all of those regions as well for assembly. Something that also really helps while you're setting up these projects is to actually add appearances to them as well. And this is just so you can get an idea for what each one of these geometry sections need to be. So what we use within Generative later on as we actually set up this project is that we'll use green for preserved geometries, which are our key pins, and we'll use red for our keep out geometries. So here you can see we have all of our key pins in green, and then the plate, the fastener locations, and the assembly clearance all within red. So showing our part again, the next section that we need to start looking at would be all of this pin location at the top. So the first thing that we might do, and again, we talked about some of those quick editing tools within Fusion 360, I might start taking away some of these fillets on that top surface. And then I would take away the chamfers as well. And the idea here is pretty similar to those pins that we worked on within that plate at the bottom, is that we just want to extract the geometry within those sections. So in this case, I might create a sketch on one of those faces, create a profile through. And then similar to those original pins that we had, rather than cutting or creating a new solid, we'll just run through an intersection, which will allow us to just extract the geometry away. So you can see that we've taken those 2 pins out and we can move those down to our preserved geometries as well. So now that's within one single component. So the next thing that we need to do is call out all of the geometry on the inside of that section as well. So if we show that original solid, we know that we can't have any geometry within those 2 pin locations. So this is a new feature that was actually added, I believe just last week or maybe the week before. It's an automatic connector obstacle tool. So in this case, the only thing that we need to do rather than creating geometry on the outside to call it later as obstacle or on the inside, we just have to select the start of the shaft that we'd like to create and then select the outside of the shaft. So here you can see it made that automatic geometry on the inside. And we can also set a clearance for the bolt head itself. So we can say we'd like to make sure we're clearing out geometry to actually apply the bolt to. And let's make sure to make that on either side. So you can see that was automatically created from that connector obstacle tool there. And then the same thing, I'll drag that new part that we created to our obstacle geometry folder. So the final thing that we would need to look at would be all of the geometry within this section here. So very similar to what we've been doing so far is I can just take one of the faces, extrude it to the other side, create a new solid for that, and then we can drag our solid to the obstacle geometry. So if we hide our part for a second, just to take a look. So really the only thing that we were doing in this process was extracting geometry that we know that we needed. So if we show our preserves, we took our original part and extracted pretty much a constant wall thickness around these pins so we can apply fasteners to it later. And then the same thing with these pins at the top. And then with the obstacle geometries, we were creating or extracting geometry to call out other parts within our assembly or fastener locations or the plate at the bottom that we know that we need to avoid later on. So when we're finished creating all of our geometry within the Edit Model workspace, we can press on the Finish Edit Model tab at the top, and that's going to bring us back to that generative user interface. So again, working from left to right, the first thing that we would do is call out our preserved geometries. So here we'd select these pins at the bottom and then the two that we created at the top. We would also do the same for the obstacle geometries as well. So we'd select the plate, the fastener locations and their clearances, and then that connector obstacle that we made at the top. So the next thing that we would need to do is start applying our loads and constraints. So again, we talked about how within Fusion, everything works from left to right. So we edited our model to extract geometry or create it where we know that we needed it. We've then called out our preserve and obstacles within the generative UI. And the next thing we need to do is actually start setting up our loading conditions. So loads and constraints can only be applied to preserve geometries where we know that we have geometry after our solve. So then we can just go ahead and hide our obstacle geometry to show the preserves. The first loading condition that we knew that we had was constraining all of the bolts on the lower plane and then applying a load on the inside surfaces of this pin towards the top. So these loading conditions were told to us through the GE project, but obviously they'd be unique to whatever project that you're working on. The first one was applying a vertical load of 8,000 pounds in the positive Z orientation. So there's a couple different ways of applying force. Here we can do it as a component in the XYZ orientation, or we can set a magnitude and then set a specific angle that we'd like that magnitude applied. So in this case, we'll say 8,000 pounds applied against the two faces that highlight now in blue. And you can see after we've set that, the force arrows are now pointing vertical the way that we'd want. So that's our first loading condition. And to get to our second, to save time, we could right click and clone that load case. And what that's going to do is create this new load case 2, which is bringing everything the same from load case 1. And in this case, rather than resetting up our constraints and our loads, we just need to change the values. So load case 2, we know has 0 component force in the Z direction, and this one is negative 8,500 within the Y. So in load case 2, we can see that we have our force arrows applied horizontally, whereas in load case 1, we can see that we have the force applied vertically. We would do the same thing to get to our third load case. So right click, cloning it, pressing to then make it the activated load. And this one is a load that's applied at an angle. So we could either apply a magnitude and then set a specific angle, or we could break it up into component forces like you see on the screen. So in this one, we'll do negative 7,060 in the Y and then 6,357 in the Z. So you can see that this force is now being applied at a specific angle. And then finally, our last force is a moment that's applied through the center of this pin at the top. And there's a couple different ways to do this, and we'll just show one of those. So we'll reconstrain all the bolt locations, and we'll then apply a force of 1,400 pounds in the Y on one face. And then on the other face, we'll just do the opposite. So we'll do negative 1,400 pounds in the Y orientation. So very quickly, we were able to set up our loading conditions for this project. Something we didn't cover here that I think is important are the other force types you can apply. So if you click on force again, you can see that we can apply forces like we've shown, or you can apply pressure as moments here as well. So very quickly to run through those loading conditions, we applied a vertical force, we applied horizontal force, we applied the force at an angle, and we applied that coupling moment where one force is applied to one face in one orientation and then the opposite in the other. So that's all that we need for our loading conditions at this point. And the next thing that we would do, again, moving from left to right, is set our objectives for the solve. So what are we actually trying to accomplish? So here we could say we'd like to minimize mass while keeping a target factor of safety, maximize the strength while reaching a specific mass target. Here we can say minimize mass while reaching a factor of safety of something like 1.5. Next would be to set our manufacturing intelligence. So we talked about this quite a bit, is the idea that we're generating models that are ready for the manufacturing process. They're models that are not just optimized structurally, but they're also optimized for the specific manufacturing techniques that we're applying. So the first option you'll see at the top is unrestricted manufacturing. And this is just saying generate me any model regardless of what the manufacturing process is. So the unrestricted option is a great way to give you ideas to then model over, just to give you an idea of what the ultimate part that you could create would be. Second would be additive manufacturing constraints. So we talked a lot about the growth of additive manufacturing and some of the values that that can provide. So within the additive manufacturing constraints, we can apply a specific overhang angle to adhere to, and then a minimum wall thickness as well. Within additive, it's going to provide you with 3 unique solutions, one that's self-supporting in the positive X, one that's self-supporting in the positive Y, and then one that's self-supporting in the positive Z orientation. And the last, and this was added just a couple months ago, are subtractive manufacturing options. So here you can set specific milling configurations for 3-axis. So here we can say what our tool setup orientation would be. And you can set what your minimum tool size would actually mill the part as well. So something else that's really important to notice within Fusion is that if there's ever a tool for what it is and you hover over it, it provides you with all that information. So here at the bottom, you can see that there's all this information to put in for minimum tool size, tool shoulder length. If you hover over any of those functions, it's going to tell you exactly what that means. So here we can add one first for 3-axis. We can also do the same for 5-axis. And we can continue to add up to 4 of these configurations, varying maybe the tool size to provide us with a range of options that we can then look at manufacturing later on. So after we've done that, we've now essentially provided it with 8 unique manufacturing options, accounting for the 3 additive options that we get, the 1 unrestricted, and then the 4 subtractive options. So we can press OK. And the next phase would be to actually start looking at the materials that we'd like to generate for. So again, moving from left to right, we'd go to our material dropdown and we could start selecting materials. So we could say, I'd like to look at aluminum. I'd like to look at titanium. I'd like to look at steel materials as well. If you click on the library, you can see you can also bring up our additive material library. So here you can say, show me additive manufacturing specific materials. And each time I'm just dragging the material that we see at the bottom up to our study materials at the top. And you can also add your own material as well. If you go to the material dropdown, you go to manage physical properties. So this is really the same idea that we just covered with manufacturing, is that we want to explore a wider range of options. So here, if we can generate for up to 10 unique kind of materials, it's very valuable for us to put in as many options as possible to then explore later on. So here you can see we now have 10 materials within this project that we can view. So now we're pretty much ready to solve. We just applied our materials, our objectives, our manufacturing types, loading conditions. We now have a pre-check that shows that this solve is ready to generate. And a new feature that was added just a couple weeks ago is this local previewer as well. So you can see at the top, I clicked on this preview at the top, and you can see that running at the bottom as well. And in about 20 to 30 seconds, it's just running a local solve to make sure everything has been set up correctly, and then to present us an idea of what some of the earlier solves or the earlier runs within this iteration might actually look like. So again, this is all prior to actually generating the part. We can get an idea of what's actually going to happen to it in the end. So if we're happy with the way that the previewer is moving, the next thing we would do is go to the Generate tab here, and that's where it would prompt you, again, like we talked about, for 25 cloud credits to generate a project, and then later on it would be 100 to load that back. So let's fast forward to where we'd have some of those results. So this is another project that I generated earlier. A project like this might take 30 minutes to a few hours. It depends on the accuracy that we're looking for and a lot of other factors like loading and the complexity of parts. After this is finished solving, we would go to this Explore tab on the top and would bring up this separate user interface that's created really to help us start to explore all these hundreds or thousands of options that we might get. So I ran this project twice, and at the top you can very quickly see that we have 160 outcomes, 141 of which converged and 19 which completed. So converged means that we've generated an outcome and it's met our objectives, so whether it was minimize mass or to hit a mass target. Completed, on the other hand, means that we've generated our part. There's no material that it can either add or subtract to continue, yet it's not reaching our objectives. So this is giving you an entire range of options to then explore. The first thing you'll notice is that you can see all of our manufacturing types that we can start to filter. So you can say, show me only additive manufacturing solutions, for example. Show me only 3-axis milling operations. You can also use the objective ranges at the bottom. So you can say, show me parts that are only somewhere in between 1 and 3 pounds. And then that's going to filter all of these thumbnails that we see on the screen. The other thing that's really interesting is that as we hover over one of these images, you can also see the entire range that this solve had to take. So it starts off with the overall volume that our part could fill. It's either adding or subtracting material away from that to reach the functional and manufacturing requirement set. So we looked at that thumbnail view. The second would be more of a properties view. So as you click to the top, you can get the entire list of properties that this part would actually adhere to. So here we can see the material type. We can see the manufacturing method. This one is unrestricted. The next one is additive, and so on. It's telling us the factor of safety target and what this reached, and some other critical information like maximum stress or the mass of this part. So as we start observing all these different components, and let's say we had a couple different ones that we'd like to look at, if we select multiple components at the same time and we press this comparison tool at the bottom, it's going to bring all four within one view that we can then start to look at. So you can see these are four unique solutions that we can then start to compare against. So the next view to look at the top would be a scatter plot view. This is taking all of the outcomes that we've created within this project and generating a graph for us to view this. So each one of these points represents its own valid, unique solution to this outcome. And here we can either filter down, start looking at the different materials. So each color represents its own material. And then we can start to find ones that we'd like to move forward with. So let's say that we've selected one from our graph, and this brings up a specific outcome view. So here we can see a timeline range at the bottom, and this is the entire range of iterations that our part has been through. So we can see when it started solving, it was taking the entire volume that this part could fill. And then as it moves from left to right, it's either adding or subtracting material away from certain sections to reach that final converged result that we can see now. We can also overlay a stress reference on this part, showing sections in green that are ideal stress reference, meaning we don't have too much material where it's too strong and overweight, or too little where it might be too weak for the stresses applied to it. We can see just about all of the generated geometry within these sections is really perfect for the case that we're trying to accomplish. And we can also view our original preserves and obstacles here as well. So if this was the outcome that we'd like to move forward with, we talked about this a couple times throughout the presentation, that the most important thing is that we're generating usable CAD geometry that we can post-process, move back into our assembly. And the way to do that is through this output tab at the top right. So as you click on that, it's going to provide you with two options. One is to create a new file from the outcome. The second is to create a new mesh. So we always recommend to create the new file from the outcome, because from that solid, if you need to create a mesh from it later on, you always can, but it's always easier to work with that solid that you can get from this model. So if we create a new file, we can show an example of what one of those outcomes look like. So it moves that file to a separate window within Fusion, and here we can start making adjustments to it. So this is one where we were looking at very specifically a subtractive manufacturing case to be milled against this face here, against the Z orientation. So when you get these generated geometries back, again, it's that idea that it's usable CAD geometry that you can then adjust. So if you're looking at this part and you think, well, maybe that strut's a little too thin, you can adjust all of that organic geometry through what we call T-splines. So just by selecting one of those faces, selecting the Edit Form tab, we can then automatically select that strut, and then we can just thicken that as much as we need. So T-splines within Fusion is a great way to adjust organic geometry that might have been impossible in the past. And then using the rest of the parametric or the solid editing tools within Fusion are a great way to fix the rest of the interfaces that we know that we need. So that went a little bit longer than I was hoping, but hopefully showing the entire process can add a little clarity to what we're trying to accomplish and how you actually get there. So I do want to leave a couple minutes at the end of the presentation for questions. So let me just recap. Again, we showed how to take our initial CAD geometry and extract preserves and obstacles, set up our solves, explore, find one to move forward with, and then post-process that final result. So again, as you're moving forward with generative technology, please feel free to take a look at our Fusion adoption portal. This has some great content on not just how to use generative, but also Fusion in general. Second would be if you're interested in trying generative on a specific project, you can use this link at the top of the screen to get a commercial trial for 30 days. And then from here, you can start trying it on your own projects. Again, please feel free to reach out to me with any questions. You can see my email on this slide on the screen, and I'll also attach it to the chat window later on. Okay, so we just have a few more minutes left, and I can stay on the call for as long as we have questions as well. So please feel free to continue to type in your questions in the Q&A or to type them in the chat window. I've also laid out some of the frequently asked questions that we get here on this slide. So I'll cover those quickly. The first one is generative available for the education community? The answer to that is not currently. Generative is only available for commercial Fusion 360 subscriptions. The second question, which we get a lot, is how much is one cloud credit? So it costs about $1 US, so it's about a 1-to-1 comparison. The third question typically is, can you trial generative? We have the link here where you can get a 30-day trial of a Fusion subscription to try it out. Another question that we typically get is, what are the solutions for generative for things like architecture and construction? We have an entire AEC generative solution, and you can see that link at the bottom. It's a little bit different from what we've been talking about today. So with that in mind, I'll start addressing some of the questions in the Q&A. Question from Mark Groves: when specifying an additive approach to the processing of material, is a solve providing a solution that is off a solid or a specific fill percentage? So that's a very good question. Generative is providing a solid outcome. Now, what you might be able to do, it matters on what kind of 3D printing technology you're using, but you could always increase that factor of safety to maybe twice as high as you know that you need, and then create an infill later on to maybe account for that. But currently it is creating a solid outcome for you. Another question, this one from Bryce: is it 100 credits to export each solid generated, or only one? So it's 100 credits to generate each solid created. And the reason behind that is it's 25 cloud credits to generate and then explore those hundreds of options you can get back. And the idea there is that maybe out of those 100, you've explored and then you've found maybe one or two that you'd like to move forward with in solid CAD. And then at that phase, you would then pay the 100 to generate that solid CAD from those outcomes. So a question from Richard: would a larger computer generate faster than others, or is it all in the cloud? It is all in the cloud, so it doesn't matter too much on the type of computer that you're using. So a few questions in the chat window. Will this webinar be available for viewing later? Yes, so this will be available on our Fusion 360 events page, and I will type that into our chat window later on. Another question from Mark: are the solve credits above the subscription costs? So yes, generative works on a consumption model. So the idea is that you would subscribe to a commercial Fusion 360 seat, which I think at most is about $495 a year. And then you would pay separately for generative cloud credits to then consume projects with. So the idea is that it's a very low point of entry to get started and to take a look at generating projects without the upfront cost of conventional topology optimization. So thank you for everyone that's asked all of these great questions so far. Let me just remind everyone that you can raise your hand too, and I can call on you to ask a question live. So another question from Micah, and I'll type this into the chat. Well, this webinar, is it available to view later? Um, it is, and let me just copy the link for you. So I'll type this into our chat window here. So within that Fusion 360 events page, you can find all the on-demand recordings and comment from Bryce in the Q&A. He wants the Rams to win the Super Bowl, which I don't agree with at all as a lifelong Pats fan. But yeah, we don't have to agree on everything. So we do have a raised hand from Steven. Steven, you should be allowed to talk now if you can hear me. Hello, Steven, can you hear me? Okay, looks like he might not have audio, but I'll remain on the line if he's able to get audio. Another question is, what is the workflow to export models from 3ds Max into Fusion 360? So that's something that we could maybe connect on offline, but Fusion 360 can import a lot of different solid CAD formats, SAT files. It can also handle meshes, but generative would not work with meshes quite the same way. So um, if it's possible, if we could connect on that offline, that would be great. So once again, thanks for all the great questions that we've seen so far. Um, I will type my email address into the chat window. If you have any additional questions moving forward, please feel free to reach out to me. And I'll also remain on the line here for just a few more minutes here if anyone has anything else. Question from Mike in the chat. I don't see the video link that you said you'd post. Am I just blind? I don't think you're blind. Let me pull that up. So as you go to the Fusion 360 events page, you'll see on demand at the bottom. When you go to on demand, you'll see generative technology in Fusion 360, and you'll see another one here as well. So as you click on that, it's going to bring you to this view tab, and here you should be able to view any video that you had. That actually just had me sign into my Autodesk information, but if you have an Autodesk login, it might ask you to sign in there. So if anyone can't find the recording, again, please feel free to reach out to me. Okay. Again, I'll remain on the line for a few more minutes. Mike, I hope I answered your question on the video there. Again, please feel free to reach out to me if you have any problems finding the video. Okay. Um, looks like no other questions are coming in at the moment. So once again, I'd like to say thank you to everyone that joined the presentation today. You can find my email address in the chat window. Please feel free to reach out to me anytime with questions on generative or how to apply it to your projects. So thank you again, everyone who joined, and looking forward to working with many of you in the future. Thank you.